Here we are. We have a matrix, a beautiful 5 by 5 matrix, and we found the largest eigenvalue using power iteration. To get other eigenvalues, we need to remove it from consideration, get it out of the picture, which we did by shifting. We shifted it to 0, it became irrelevant. However, the shift trick only yields another eigenvalue, and that's it. It cannot yield more. So we need another trick, how to neutralize this eigenvalue. And this is the moment when we take inspiration from the world of operating systems. If you remember, we had this complication that the initial vector perhaps does not include this direction or that direction, and it could hide some eigenvalues from us. Well, we are going to say, well, it's not a bug, it's a feature. Yes, we can actually make some directions disappear by smartly choosing initial vector. So, I have my eigenvalue, I have my eigenvector, and if I choose my initial vector so that it does not feature this direction, then the iterating procedure, the power iteration, will not see this eigenspace anymore, it will not see this eigenvalue anymore, and if I run power iteration, it should find the second largest eigenvalue. That sounds like a neat idea, which can be recycled. We can remove more directions by smartly choosing the initial vector. Okay, how do we do it in practice? We have a nice vector here, we found it, our first eigenvector. How do I find initial vector which does not feature these components? I actually did a trick like that before. I used initial vector which combined the other directions. But the problem is, normally I don't know them. I just know this direction. How do I find a vector which does not use it as a component? Well, let's have a look at a simple picture. Here is my vector v1, the first eigenvector. And I'm wondering, okay, how should I choose my x0? And you may think, why don't you take a vector which is perpendicular? Okay, here is my vector which is perpendicular. This could be x0. Does it use the component v1 or not? And the answer is, I don't know. Nobody knows, because it all depends on v2. Let's imagine that v2 looks like this. This is v2. What is the decomposition now? We have to use parallelogram, whatever they call it, like that, like that. And this is the decomposition of vector x0 into our basis. And we can see that this vector is actually a sum of these two components, and we are using component v1. We didn't avoid it. So unless we know all the other vectors in the basis, we are unable to create x0 which does not use direction v1. So this looks like a dead end. It's not a dead end, but it's something which forces us to restrict our attention to matrices that are, in a way, nice. So I'm going to look at matrices now A, which have this property that when you look at the eigenvectors, they not only form a basis, but they form orthogonal basis. What does it mean? It means that all the vectors are mutually perpendicular. And in such a world, in a space with such a basis, orthogonal basis, this trick with perpendicular x0 will work. And therefore, in such a world, we can do the following trick. We use power iteration to find the largest eigenvalue. Lambda 1, v1. Then we choose some initial vector x0, which is perpendicular to v1. We run power iteration, and we get the second largest eigenvalue. Or perhaps not. If there is a tie, then we shift the matrix. We know how to do these things. We don't have to worry. Then we find an initial vector which is perpendicular to v1 and also to v2. Let me put it like that. I should put x0 perpendicular to the span of these two vectors. Okay, it's okay. And we get the third largest eigenvalue. Or perhaps there is a tie and so on. Let's ignore the details now. Then we find x0, which is perpendicular to v1, v2, v3, and these are all vectors. And we get lambda 4 and v4. And we keep going until we find lambda n, vn. all the eigenvalues. Theoretically, perhaps, we will see. Does it look good? Yes, it does look good. Now, what are the chances of actually having orthogonal bases when you get a matrix? And the answer is, well, there is this theorem, this fact that I recalled from linear algebra. If your matrix A is real and symmetric, then you do have a basis of eigenvectors, orthogonal basis of eigenvectors. So this is really something that does happen in many examples. And our 5 by 5 matrix, let me go back to it. Let me see, over here. Our 5 by 5 matrix is real and symmetric. So eigenvectors do form an orthogonal basis, and you can actually check that these 4 guys over here are mutually perpendicular. There is a 5th guy missing. We will see. How does it work now? We start power iteration, and I can use the same vector that I used before, and I'm not doing any shifts or inverses. This is exactly what we did before. We run power iteration with some x0, and we get the largest eigenvalue. So the initial vector, okay, somewhere here. It's some vector, I'm not going to write it. The important thing is power iteration provided us with lambda 1, which is negative 60, and vector v1, which is 0, 1, 0, 1, 0. Okay, I'm going to use row notation to save some room. What next? Well, we need to find initial vector x0, which is perpendicular to this v1. Now, perpendicular means I have 0, 1, 0, 1, 0, and I'm looking for a vector which works like that. When I multiply the corresponding coordinates and then sum up, I should get 0. Well, the easiest way to do that is to put 0 here, and now it's guaranteed that these 2 guys will be perpendicular no matter what I put over here. So just to make my life easier, I put 0 here, and okay, I want something there. I cannot take 0 vector, so I put, let's say, 1 here, 1 here. Is it a nice vector? I hope so. So my next initial vector will be 1, 0, 1, 0, and 0, and I apply power iteration to this initial vector and matrix A, no change to the matrix. And when I do that, okay, I feel sorry that I have to remove those 13s actually, but okay, that's life. I could use vector 13, 0, 13, 0. Okay, let's leave it like that. And we are getting 36 for the eigenvalue, and the eigenvector seems to be really 1, 0, 1, 0, 1. So far, so good. So now we have 2 eigenvalues, 2 eigenvectors. Lambda 2 is 36. V2 is 1, 0, 1, 0, 1. And we are looking for eigenvector that would be perpendicular to these 2 guys. Okay? Let's see. 0, 1, 0, 1, 0. 1, 0, 1, 0, 1. I'm looking for a vector which is perpendicular to this one and also to this one. So I'll handle this guy first. I put 0 at the 2nd and 4th coordinate, and now these 2 guys are perpendicular. How about these 2 guys? For instance, I can put 0 here, 1 here, negative 1 here. Okay, so our next initial vector is 0, 0, 1, 0, negative 1. And we use it to start our power iteration. And actually, with negative 60 and 36 out of the picture, I expect to see an infinite loop. Definitely. Let's have a look at it. I'm changing the initial vector to 0, 0, 1, 0, negative 1. And I'm getting infinite loop. Okay, what do we do with this? The answer is, well, this tells me that there is a tie for the next largest eigenvalue, so we shift the matrix. Okay, let's shift the matrix. So we are actually using the operations after all. Matrix is shifted, let's say by negative 1. I'm going to shift it to the right. And I'm getting negative 60. How come? How is it possible that my power iteration actually provided me with eigenvalue and eigenvector which is perpendicular to the initial vector, because we can see the eigenvector here. It's essentially 0, 1, or 0, negative 1, 0, negative 1, 0. That's perpendicular to this one. How is that possible? And the answer is, this idea is very nice. This whole idea about perpendicularity, things like that. But it only works theoretically, or it works if we do the calculations precisely. For instance, if I forced my system to work just with integers and rational numbers, then these calculations would actually work. But my system is working in the floating point form, and therefore there are some rounding errors. And because we have rounding errors, then these vectors xk are not exactly what they're supposed to be, but they're slightly different. And because they're slightly different, this forbidden direction actually found its way into my vector. And it was there, and it was very, very tiny. And this iteration stopped very early. It was like 12 iterations, if I remember. So this was a very short run, and even though this dominant direction found its way into this one, I'm sure about it, it didn't have time to assert itself, to appear in the output. But here the run was longer, it seems, and therefore our forbidden direction, the dominant direction, had a time to reassert itself, to show its dominance, and it won. So that's actually a serious concern. That's a big problem for all these methods, and especially for methods which actually use this trick with perpendicularity with forbidden directions. This is a big problem. We need to somehow solve it. And we actually have more motivations for that. Let's imagine that by some miracle this would actually work, or perhaps with a better system. I can imagine that if I ask for double precision or triple precision, then perhaps we would get another eigenvalue, most likely 12 after a shift. We do it a few times, and then we have like 4 vectors. And we need to find a vector which is perpendicular to these 4 guys. How do I do it? Well, it's no longer going to work like that I just look at them and dream it up in some intuitive way. So this is a very serious concern. This procedure is very nice while you are here, looking for perpendicularity to 2 vectors, 1 vector. This is okay. 3 vectors, this is already an adrenaline sport. 4 vectors, 5 vectors, this is really bad. You could use some trick from linear algebra. Essentially, you would choose a vector by random, and then you would use the Gram-Schmidt orthogonalization process, whatever it's called. But actually, when you think about it, there is the same problem in the iteration and also at the start. In each case, we have a problem that there are some directions which are not wanted, and we want to get them out of the game. So we can actually use the same trick throughout the iteration, even at the very start. We have the initial vector x0, and perhaps we choose it randomly, and we need to remove the unwanted directions. And then, as we are doing this iteration, the power iteration, at each stage, we would actually look at this vector xk and again remove the unwanted directions. And if we can do that consistently, then we would get a procedure which actually makes this whole trick work. Okay? Let's have a look at it. How do we remove unwanted directions? Key question. Well, we have to use projections. And the projections, you think back to linear algebra again, they are much easier if the vectors have norm 1, Euclidean norm 1. So there's another assumption. We actually want orthonormal basis, which means that the vectors are perpendicular mutually for I not equal to j, and the Euclidean norm, which is you square the coordinates, sum up, square root, the usual stuff, the Euclidean norm should be 1 for all I. So that's my new assumption. And with this assumption in place, we can do the following trick. When somebody gives us a vector xk, we subtract the projection of this vector to the first coordinate, to the first eigendirection, which is v1. How does this projection work? We have to find the inner product of our vector with this direction, and then this will be a number, and this number essentially describes how much of this vector is in the direction v1, and then we take this and subtract it. So that's the component of vector xk in the direction of v1. And then we, of course, subtract for the second vector and so on for all the vectors that we already know. So if we know lambda 1 through lambda n, some eigenvalues, each one having some eigenvector, then we are subtracting all the way to xk inner product or dot product vn, vn. So that's an operation that we can do at every stage of our iteration, including the stage 0, when we are just guessing the initial vector. Let's give it a spin. Okay, so I have a code here. See, because we are reaching into the iteration, this should be a part of the iterating step. After we modify, then we do the remaining part of our iteration. We multiply by matrix A, we divide by this approximation of lambda, and so on. So really reaching into the procedure, I have to do it by hand. So here is the first run with lambda 1 being negative 60, and the eigenvector, if I see it correctly, is 01010. 0101 and 0. Okay, so the next step is a check that what we inputted is really the eigenvalue and eigenvector. So we expect to see vector with 5 zeros on the output at this stage. Then I'm normalizing the eigendirection, the vector v1, so that it has norm 1 in a Euclidean norm. Then I set up the initial vector x0, and I'm actually recycling the same vector that I used before for the first run. I'm not adjusting it to be perpendicular to anything, because I know it will be taken care of with this term. I'm going to remove the unwanted directions anyway, so I don't bother here at this initial stage. Here we go, that's my initial vector. And now here this code essentially is just one step of power iteration. So for instance here, you can see the Rayleigh quotient. We are estimating the eigenvalue here. And over here you can see that I take x that I iterate with, and I subtract the projection onto the direction v1. So that's exactly this code, just with v1. Okay, let me run it once. So that's the outcome of the first iteration, and that would be actually the first row if I use the power iteration procedure that I have here. Okay, but I cannot use it. I sort of reached into it. I'm messing up with it. So I run it a few times. Second, third, fourth, fifth, 6, 7, 8, 9, 10. So I ran it 10 times. Do I see some convergence? Perhaps yet. Yeah, okay, let's be on the safe side. Let's run it a few more times. So it seems that we are really getting eigenvalue 36. I can see it there. Nice convergence. And when I look at the vector, eigenvector perhaps, I can see 1, 0, 1, 0, 1. Yeah, that's exactly this guy, the second largest eigenvalue. So the trick with removal seems to work, but now it gets interesting. I have two forbidden directions. Let me input the second one. So the eigenvalue is 36, and the eigenvector is 10101. 10101. And again, I'm going to check that my data is correct, normalize v2, and set up the first iterating vector, the initial one. So it's actually the 0th vector. And now again, I'm going to use power iteration, but this time there will be two projections, because I'm removing two directions. And you know what? Let me start with this guy, because that was a good attempt. 0, 0, 1, 0, negative 1. Let me start with that one. I could actually start with the initial vector that I'm using always as a default in this example, but let's have a look at this. What happens to this run if I do not let this first two dominant guy interfere with my iteration? So here we go, that's the initial vector. And now let me run the iteration a few times. So we can see here that we should be getting eigenvalue 12, or perhaps not, because there are two competitors now. And when you look at it, the eigenvalue pretends to be 9, but we know that it's nonsense, because when we look at the vectors, this is definitely not a convergent situation. In fact, we see a cycle. Okay, so we remember we have a vector which is essentially half, 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 negative 1. And I do two iterations, and we have the same vector. Half, 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 negative 1. We are in a loop. So if I actually shift, everything works the way we expect it. If I shift it, and if I try this by hand, It does seem to work. So this removal trick is really the key to success for this idea with perpendicular initial vectors. However, as you could see, it's a lot of trouble. I could write down a new procedure which does it, but this is too much work. All those projections, all those calculations, too complicated. There is a way to do it in a much more elegant way, but to get there, we need to do some black magic. Let's have a look at it. I take this vector and I just give it a name, temporary name. Let's call it Z or Z. And what I'm going to do, I'm going to have another look at these projections. This expression can be written in a different way, in this way. I take vector v1, I do the usual matrix product. This is the dot product or inner product. This is the usual matrix multiplication with vector v1 transposed. And use this to multiply the vector xk. How do I know that it's the same? I never learned such a thing in my linear algebra classes. This is a very specific formula, but it does work. Let's think about it. What is this animal over here? This is a vector which is a column vector. And we use the usual multiplication, matrix multiplication, to multiply it with transposed column vector, which is a row vector. It looks like that now. What do we get? Well, we are using the matrix multiplication, so we are trying to go by rows, by columns. How many chances there are? Well, there are many possible combinations for our multiplication. We can choose different rows, different columns. In fact, the output of this is an n by n matrix. And you can think of what the entries are. For instance, the upper left entry is obtained by the first row, the first column. This is v1, v1. The second entry in the row is the first row, second column, v1, v2, and so on. So it's possible to work out the terms of this matrix. And now this matrix, this n by n matrix, multiplies a vector, which is a column vector. So it makes sense, and the output is a vector. And this is a vector, so we can subtract. It all makes sense. And when you multiply this matrix by vector xk, x1, x2, and so on, and you check out the output, and you compare it with this, you will see it's the same. Okay? So really, these two expressions are the same. Although it looks like a black magic, it's actually proper mathematical work. And what's the advantage? You will see in a second. Okay, I'm going to do it everywhere. Vn multiplication, Vn transpose, xk. One advantage is that now we have two matrix multiplications, so we can drop the bracket. It's just a group of 3 multiplications. And it becomes even more interesting when I take this vector and multiply it from the left by a. Why do I want to do it? Because that's the power iteration. You take your iterate vector, xk, multiply it by a, and divide by the lambda approximation. So let's not bother with lambdas. Let's have a look at az. Well, I'm multiplying by a, vector xk, minus, and now I'm multiplying by a, and that's also a matrix multiplication, so I have to be careful. I cannot rearrange the order. That's forbidden. So a has to come here at the start. A v1, v1 transposed, xk, minus, and so on. And this is happening everywhere with all projections. And now here comes the payout, the payoff, the great moment. First of all, I'm going to factor out xk because that xk is just multiplied in the usual vector multiplication from the right at every term, and distributive law works actually. So xk comes out. That's very nice. In the original formula, xk was sort of hidden inside inner products. I wouldn't be able to do that, but now I'm able to pull it out. That's very nice. Okay, let's have a look at this expression. I'm factoring out, and here AV1, V1 is an eigenvector, so AV1 is essentially lambda 1, V1, and then V1 transposed, and so on. Now, does it make sense? V1, V1t is a matrix. We talked about it. So it's a matrix which is multiplied by a number, subtracted from a matrix. This does make sense. This creates a new matrix. And in the same way, I go all the way to the last term. So what we see here is the heart of the power iteration step. You have your vector xk at the start, and in the usual power iteration, you would simply multiply it by a and then divide by lk. Okay? What we do here, we insert this intermediate step with projections, but when we look at the formula, we can see that actually we can store those projections in the matrix. This is a new matrix B. And if I forget about this modification of matrix A, this looks like the usual power iteration because I take the vector xk and I multiply it by a matrix, the new one, matrix B, and then I divide by L and do all the stuff. So the trick is that if you want to use those projections, the removal of unwanted directions, you don't have to do it manually inside your power iteration. Instead, you simply change your matrix. And then you apply the usual power iteration to this B. And that's finally the version which works in applications, which makes sense, which is even convenient because you are just changing the matrix. And this actually has a name. This is called the deflation method. And let's see, it's the last slide for today. So that's usually good news. It's almost over. Let's see, what does it say? It says we have a matrix, we have eigenvalues and eigenvectors, and we assume that the vectors are normalized with respect to the Euclidean norm. Then we set up an auxiliary matrix, B, which is A, and also the projections included. And then we run power iteration, and we obtain the next largest eigenvector, or perhaps there's a tie, then we shift, whatever. Let's not worry about technical details. So that's the deflation method. Now, notice that for the eigenvectors, we want them to have norm 1 with respect to the Euclidean norm. Now, there is also normalization happening inside the power iteration, and typically we would use the infinity norm. But having two different norms, it doesn't look really good. It's not consistent. It's not a problem, but it's an extra work. If you use Euclidean normalization in power iteration, then the v's which you get out of it, these guys, will already have Euclidean norm 1, and you can directly use them in the deflation trick. So when we go back to our 5 by 5 matrix and try to run this example again, I will actually use normalization with respect to the Euclidean norm. I will do another thing. Let's go back to our code. Here is our matrix A, and we start by running power iteration. And notice, this time I'm using normalization with respect to norm 2. So the output, the eigenvector, should have norm 1 in Euclidean norm. Let's have a look at it. Previously, we got vector almost 0, 1, 0, 1, 0. But this time we don't have 1s, so that the norm is equal to 1 in the maximum norm. But instead, we have something like 0.707 and so on. This is essentially half of the square root of 2, by the way. Something that you have to do so that the norm of the vector has Euclidean norm 1. Okay? But otherwise, negative 60, that's the largest eigenvalue. Everything works. And this brings me actually to the last important point of today's talk. I was worried about numerical errors. That's why we do this removal. How about here? Perpendicular vectors. This is very extremely sensitive to numerical errors because you have two vectors that are perpendicular. Now, if you change one of them, even slightly, even tiny change, they are no longer perpendicular. And that's where the trouble starts because, okay, we have vectors v1, v2, and then we find something, we are removing projections over here, but we are actually not removing true eigenvectors, true eigendirections. Why not? Well, all these problems that I did today, I was actually cheating. These are school problems with really cute answers, integer-valued answers. But in real life, somebody gives you a matrix. And you don't know that the eigenvalues are going to be integer-valued, and you don't know that the eigenvectors will have a nice representation. You are just getting some vectors. You don't know what to do with them. You look at this vector, there are some numbers, and you have to keep them. Because you cannot just make them nicer. You don't know that your matrix has nice answers. So in this run, now that I'm going through this example, I'm actually not going to cheat. I'm going to keep exactly the output that I get from my procedures. So for my lambda, I get negative 60. Okay, I do get. And for my vector v1, I get exactly this animal. And you can see that instead of zeros, there will be 0.1 1, 2, 3, 4, 5 zeros, 2, 6, 9, something like that, okay? So let's see. I'm keeping the output, and I prepared my new matrix B using the projections. And you can also notice that I commented out the normalization step because my vector is already normalized with respect to the Euclidean norm. And now I'm going to run power iteration with this matrix B, and I keep the initial vector as before, my favorite, okay? Lots of 13s, I love it. And again, I normalize with respect to the Euclidean norm. And let's see what we get. We are getting 36, which is the second largest eigenvalue, so this works. How about the eigenvector? Do I see zeros on the second and fourth position? I essentially see zeros. Do I see ones? I see 1, 1, 1. Well, I see the same numbers. So if I normalize with respect to the maximum norm, I should get 1, 0, 1, 0, 1, 0, 1. So yeah, this is the right direction. Let's store it. Let's store the imperfect versions. This time, my new matrix B is actually A modified with 2 directions. I'm removing 2 unwanted directions. So I know these 2 guys, and I'm asking for the third one. Okay? Let's see. I run this new matrix B with the same initial vector as before, and so on. And I can see that we have a cycle because we are not surprised, because we know that there is competition, but even if we didn't know it, we would see it here. There is actually infinite loop. And when I look at, let's say, at the 5th coordinate, I can see that every second vector is essentially the same. Okay? So yes, we have a loop. We have to shift our matrix. So I'm shifting the matrix slightly. Let's say by -1 to the right. Okay, no problem there. And I get eigenvalue 12, perhaps. And now, how about the eigenvector? I can see that the 3rd coordinate is twice as large as the 1st or the 3rd, which is exactly the case over here. And there is the opposite sign, okay? So this ratio seems to fit. And I can also see that the 2nd coordinate is halfway, in absolute value, halfway between the 1st and the 3rd. 3 is halfway between the 2nd and 4th. 2nd and 3rd, okay? So the vector that we see over there should be parallel, should be the same direction as this guy, okay? And you can check if you take this vector and divide it by, well, divide it by the 1st coordinate and multiply it by 2, and you should get it. Okay, let's play. Before I do it, let me just store the results. So my results are stored as L3 and V3, and I set up a new matrix B, which is essentially, again, I'm removing 3 directions now. I could use the opposite shift if I wanted to get at number 12, -12. But I'm following the deflation algorithm. I have 3 vectors, so I'm going to remove them. Now I'm removing also the 3rd direction. Okay, before I get there, let me make an intermediate step. I'm curious. I take the vector V3, I multiply it by 2, and I divide it by the 1st coordinate. What do I get? And I'm getting vector 2, -3, -4, 3, 2, essentially. Okay, so my vector, my eigenvector V3, is a good approximation of this direction. Well, not all that good, but it's reasonably close. Okay, so let's run my power iteration again. I'm not shifting anything now. I simply keep my initial vector as before. I take this B, which is now removing 3 directions. It's removing this direction, and this direction. Perhaps I should make a note of it. So this one is gone, this one is gone, and this one is gone. Let's see. Wow, that was short. Let me return to it. Why is it so short? Okay, we are getting -12, which seems to work. And we are getting a vector where every entry, apart from the last one, seems to be 1/2, more or less. If I multiply by 2, I get 1, 1, -1, -1, 0. So again, this seems to be the right direction. So let's ban it. We discovered everything that we knew before, it seems. And now it gets interesting. So I'm going to store this output. I'm going to prepare the last auxiliary matrix. I take A, and I'm removing first direction, second direction, third direction, fourth direction. There is just one direction left, so we should get the result. Let's see. Bang. Okay, we've got eigenvalue 12, an eigenvector that looks, well, that's a good question. How does it look like? Okay, I think that the first coordinate is a triple of the second coordinate, roughly triple. Yeah, it seems like that. And the last coordinate is about 4 times the fourth coordinate. Let me divide this vector. So this vector, let me store it first. It would be v5. So I'm going to store it like that. Is that right? Yeah, it's that right. And now I take v5 and divide it by the second coordinate. And we are getting vector 3, 1, negative 1, negative 1, 4. Is this the eigenvector and 12 the eigenvalue? That's a good question. So let me just check that A times this vector minus 12 times this vector should yield 0. Is it true? Yeah, essentially yes. We are getting essentially zeros. So really, negative 3, 1, negative 1, negative 1, 4 is an eigenvector, and it's a different direction from this one, which shows that 12 is actually eigenvalue of multiplicity 2. Finally, we found the answer. Finally, we know everything. So here for 12, I'm actually adding another eigenvector. Let me change the sign so that I start positive. It's always good to start positive. Negative 1, 1, 1, negative 4. Here we are. So we know the complete list of eigenvalues with their eigenvectors. Everything is wonderful. Let's return back to the question of runs. Okay? This last run was fairly short because there was essentially just one direction left. So the iteration just needed time to find it. And it found it fairly easily. The second last run, this one is suspicious. Let me go back to it. Why is it suspicious? Well, let's think back. What does it mean, the third run? The third run worked like that. We removed this direction. We removed this direction. We removed this direction. And now we are running the auxiliary matrix. What were the eigenvalues? Well, we removed this direction, but now we know that there was another 12 appearing still in the game. And there is also negative 12. So how come that we didn't get an infinite loop? That's what we would expect, actually. Now that we know all the information, we know that 12 is there twice. If you remove one of them, the second guy is left in the game. Why didn't we get a tie? Instead, we got very quick result reading negative 2. And the answer is we got extremely lucky. Sometimes you do get extremely lucky. The very first direction that we got, after it got multiplied by matrix A, then accidentally, we already got the eigenvector. So this was algebraic luck, extreme algebraic luck, because the chances of this happening are almost nil. And because the procedure found the eigenvector for negative 12, it stuck with it. And it said, oh yeah, I got it. So we were really lucky. If we were not this lucky, if I change the initial vector just a little bit, how about if I change the last coordinate to something random, like 13? Yeah, totally random vector. So this time we will not be that lucky. You cannot get this lucky twice. So if I multiply this new initial vector by A, I'm pretty sure, almost sure, that we do not get eigendirection out of it. And that's why the iteration will have some room to play. It will discover that there are two competitors for the largest eigenvalue. I expect to see a loop, infinite loop. And I do. Okay. When we look at the last coordinate, we can see that every second vector is the same. So yeah, things behave as advertised, which is wonderful. So much for this remark. Let's go back to the example. What did we just see? We saw deflation method in the efficient way implemented by changing the matrix. And it worked like a charm. It took our 5 by 5 matrix and it found all the eigenvalues, all the eigenvectors. Even though one eigenvalue was of higher multiplicity, the procedure found everything. It did even survive that we didn't cheat. We didn't round these answers to something nice. We used it as it came from the procedure. So we used approximate eigenvalues, approximate eigenvectors. The procedure still handled it beautifully. So this is a very robust procedure. Deflation, wonderful. Let me show it again. Let me part with it like that. Okay, so the deflation procedure, that's the happy end. It doesn't get any better in this course, so this is the best time to stop. Hope you enjoyed it as much as I did. And see you next time. But this guy is perpendicular to my starting vector. I didn't write it down. I'm a moron. That's the happy end. It doesn't get any better, so this is the best time to stop. Hope you enjoyed it as much as I did. And see you next time. Did I forget something? Anything? Let's see. I said this. Okay. I guess I said it all. We are done. Okay.